All right, welcome back everybody. In today's video, Applied Optimization, we're going to take some of the skills that we've learned in prior sections like 4.3, maximum and minimum, and apply them to something real. So we're going to do more of a real world application type section here. I'm going to take you through a couple of different situations. There's just not enough time to take you through every situation you'll encounter. But hopefully after this, you'll have a good start as to how to attack an applied optimization problem. The key with applied optimization is that all of these are real things, which means that for the most part, you're going to have a limited domain on most of your problems. So we're going to use that limited domain to our advantage. Let's take a look at the first example. An open top box having a square base and a surface area of 108 square inches. What dimensions will produce a box of maximum volume? So a pretty basic one to start. We're just talking about a box. We want to build a box, surface area of 108 square inches, and we want to maximize its volume. All right. So I'm going to quickly sketch a box. I like making a sketch even though I'm not that good at it. Kind of helps me in the sense that this is something real. Yeah, I've made better boxes in my day, but pretty good. Square base means that we have X and X over here. And to get my volume, I also need my height. All right. So let's start out by writing down things we know. The volume of a box with a square base is just going to be length times width times height. And if the length and the width are both x, the volume is going to be x squared times your height. And this we're going to call our primary equation. So this is our The reason this is our primary equation is what we notice is we have two letters here. We have two variables. We have x and we have h. Number one, we're in single variable calculus, which means we can only have one variable. And second of all, if we have two unknowns, we need two equations. So we need to figure out a secondary equation that we can use to help us solve our primary equation. Well, the problem usually gives you a reference as to what your secondary equation might be. Okay, your primary equation is always going to be in the question of what's asked. What dimensions will produce a box of maximum volume? There's your primary equation. All right. Usually in the problem, there's a hint as to your secondary equation. So a surface area of 108 square inches. So let's try to use that to say surface area equals, well, I have the area of the bottom is x squared, and the area of each of the faces is x times h. So I'm going to say plus 4x times h. And in the problem, we said it was an open box. Right, which means that there's no top, hence there's no surface area for the top. All right, and this equals 108 square inches. All right, so now it's a matter of a little bit of intuition, a little bit of experience, but a little bit of common sense as well. I want to keep x as my variable. And I want to get rid of the h. There's less h's everywhere. So I can solve my surface area for h. So why don't you do this right now? Why don't you pause the video, take a moment to solve my secondary equation. I'll call this the Why don't you solve the secondary equation for h, and then we'll talk about it on the back end. Okay, hopefully you solved it. Let's take a look. So I have 108 minus x squared equals 4xh. And then I'm going to divide by 4x. So I get h equals 108 minus x squared over 4x. And what I can do is I can take this and plug it in over here. Okay. Now, again, one of the reasons why I chose to substitute in for h is because if I substituted in for x squared, whatever I got for x, I would have to square it, which makes things more difficult. So here I can just substitute in and then just kind of get going. All right. So let's see. We have volume equals x squared times 108 minus x squared over 4x. All right, so why don't you do some work, do a little simplifying, and then we'll talk about it on the back end. All right, hopefully you took a moment to simplify. When I simplified this equation, I wound up with v equals 27x minus 1/4 x cubed. All right, and now we need to take a look back at the problem to figure out our domain, because our domain is definitely limited. I'm going to take away some of these markings. All right, so we have a box with an open top with a square base and a surface area of 108 square inches. All right, so if our height was 0, everything would be plugged into x. Right? So x could be as small as 0 because it's a box. It's something real. You can't get a length less than 0. So 0 is our minimum. But if I what if I said h equaled 0 in my secondary equation? I would get x squared equals 108. So x could only be as big as the square root of 108. All right? So this is kind of a leap to say my height is 0. That's a pretty lame box. But it's possible because we could have a height of 0. So that means all of my surface area pumped into the square base. So the biggest my x could be would be square root of 108 because they said that the surface area was 108. So my domain is going to be 0 less than or equal to x less than or equal to the square root of 108. This is going to come into play a little bit later. All right, let's start by getting some critical numbers. So if we do dv dx, we get 27 minus 3/4 x squared. And we're going to set that equal to 0. And then I'm going to say 3/4 x squared equals 27, and multiply through by 4, so I get 3x squared equals, not 81, just kidding about that, 108. X squared equals 36, and x equals plus or minus 6. Now, question, can we have a length of -6? The answer is clearly no. That is impossible in our real world. Therefore, we could say that +6 is the critical number. That's a really bad N. The critical number. All right. We take -6 and we discard it as impossible. All right. So we're going to do it just like we were doing our increasing, decreasing on a limited domain, right, to get our max and min. So what I want now is I want to know v of 0, I want to know v of 6, and I want to know v of the square root of 108. All right, and what you do is you go back to the original equation, All right, our volume equation right here. All right, and I want to know, or actually, you know what? Probably right here because we have x and we don't have h. So go here. I agree. And plug in your numbers and then tell me what you get. All right, so pause the video, plug them in, and we'll check our answers on the back end. All right, so when I plugged 0 into that equation with all the x's, I got 0. When I plugged 6 in, I got 108. And when I plugged in the square root of 108, I got 0. That means that right here is our max. So our max is when x equals 6. The only question is, what does h equal? And for that, you could go back here, plugging in 6 for x, right? And figuring out h. So why don't you pause the video, find out what h is, and then you can write out your dimensions, because your dimensions will be x times h. X by h. So go ahead. All right, hopefully you figured it out. I got h equals 3, so dimensions 6 by 6 by 3. And one of the keys to this is organization. So when you're looking at these, do your best to keep yourself as well organized as you possibly can. All right, so let's take a look at the next one. The next one is we're going to try to find a minimum distance, all right? So pretty straightforward problem. Which points on the graph of 4 minus x squared are closest to the point 0, 2? So my equation is y equals 4 minus x squared. And I want to know what points are closest to 0, 2. All right, so we're looking for a minimum distance. Hence, we want to know, we need to use our distance formula. So d equals the square root of x minus 0 plus y minus 2. I'll put squareds there. And I'm getting the 0 and the 2 right from my problem. This is my primary equation. Now, the problem didn't really give us a clue for a secondary equation. The only clue we have is we need to use distance. Okay? So I'm going to reuse the distance formula for my secondary equation. However, I'm going to do something a little different. See this? This is what y equals. So I'm going to take this, and I'm going to substitute it in right there. And let's see how that works for me. All right? So I'm going to take that away because I want a little bit of... all right, so my secondary equation is going to be d equals the square root of x minus 0 squared. I'm not doing anything to that, so I just want to call that x squared. I hope that's okay, because I'm going to have a little bit more with the next one. So then I have 4 minus x squared. All right, so I'll say plus over here. Minus 2, the whole thing squared. All right, so why don't you take a moment and let's simplify this equation, this secondary equation. And when we come back around, we can square up our answers. All right, so I got, when I simplified, the square root of x to the 4th minus 3x squared plus 4. Hope you got the same thing. If you did not, go back and double check. This is indeed correct. Now we're looking for the minimum distance, all right? So d is the smallest when the stuff inside the square root symbol is at its minimum. So the square root symbol really has no effect on getting our critical numbers. So we can ignore it, yay for us, and just use x to the fourth minus 3x squared plus 4 to find our critical numbers. So my derivative is going to be 4x cubed minus 6x, and I'm going to set that equal to 0. And I'm going to ask you to solve for the values of x. So pause the video, solve for my values of x, and then we'll check to see if our critical numbers match up. All right, so hopefully you solve for x. I got 3 different answers. I got x equals 0. I got x equals the square root of 3/2. And x equals the negative square root of 3/2. All right, now you need to do the first derivative test. All right, you got to set up your intervals just like we did before. If you don't remember the first derivative test, go back to the prior video with that title and work on it. All right, so why don't you do the first derivative test? When we come back, we can talk about which values are our maximum, which values are our minimum. All right, so hopefully you did the first derivative test okay. Hopefully if you needed a little extra, you went back to the other video and saw that you should set up that chart, interval, test, sign, conclusion. All right, I got that x equals... So, well, I can just use these. That's fine. X equals 0, I got as a max. And I got this as a min and this as a min. All right. So if we take our 2 minimum x values and we plug them back into our original equation, right, over here, we can get the y values because we need to know which points on the graph, right? So we need an x and a y value. All right, so why don't you do that? Take these 2 values, plug them back into the original equation, get the y values, and we'll talk about it on the back end. All right, so I got as points the square root of 3/2, comma 5/2, and I got negative square root 3/2, comma 5/2. All right. So now we're going to talk about a rectangular page containing 24 square inches to print. The margins at the top and bottom are to be 1.5 inches, and the margins on the left and right are 1 inch. What would be the dimensions of the page? So the least amount of paper is used. All right, so once again, I want to draw a very quick picture. There's my paper. Now remember, not every inch of this paper is printable. So I'm going to make a smaller rectangle of my printable area. And then we can see the margins at the top and bottom, the margins on the left and right, and we know the values there. So if the left and right are supposed to be 1 inch, right? 1 and 1. That means that's a total of 2. So I can say area equals, right? And that's 1.5 and 1.5. So I got, so let's say this is x. Let me think. Let's say this is y and this is x. So my printable area is xy. But if I wanted to do the total page, I could say it's x plus, well, hey, you want to do that one x, and I'll do this one y, right? Because x is vertical, x is horizontal, y is vertical, or something to that effect. All right, so I got x plus 3, right? I had it right the first time. All right, losing my train of thought. So x and y. and y plus 2. It doesn't matter which one you use for x and y, as long as you have the corresponding margin. So I've got y over here, and I got plus 1 and plus 1. I got x over here, plus 1.5, plus 1.5 will get you 3. So as long as you're consistent, it doesn't matter which one you pick for x and y. All right, so we said my printable area is going to be x, y, and my printable area is going to be 24. So this is my so I've got my primary and my secondary equations. Now I'm going to solve my secondary equation for y. Y equals 24 over x. And now I can take that and plug it in for y in my primary equation. So I have area equals x plus 3 times 24 over x plus 2. And I want to multiply that together. I did that quickly, so I'll say it's just 30 plus 2x plus 72x to the negative 1. You're always welcome to check my work. I have no problem with that. The reason I wanted it to look like this is because I can use the power rule for my derivative, because now we need to find our critical numbers. So we have dA over dx, and that would equal 2 minus 72 over x squared. I'm going to set that equal to 0. And now we need to solve it. So why don't you go ahead and solve this for x, and let's see where we're at on the back end. All right, so hopefully you solved it. I got x equals 6, x equals negative 6. Once again, negative 6 gets crossed out because we're talking about area, we're talking about lengths, and we can't have a negative length, all right? So now that we know that there is only one critical number, all right, do your first derivative test once again and see if you get a max or a min. All right. So if you did your first derivative test, remember you had a limited domain, right? Because your printable area was 24. So I got 6 is a minimum. All right. So if I wanted to find out y, I could say y equals 24 over x. So I plug in 6 and I get 4. So my dimensions would be, right, if I had x plus 3, right? So it's 6 plus 3, so that would equal 9. And y plus 2, right? Those are dimensions of the paper, so 4 plus 2 is 6. So I got 9 by 6 as my dimensions. All right. So one last problem we'll do quickly. I know I've kept you for a while, but that's okay. We'll knock this one out, and it'll be fine. 4 feet of wire is used to form a square and a circle. How much wire should be used for the square? How much should be used for the circle to enclose a maximum total area? All right, so we need to start with area equations. I've got A equals, the area of the square is just going to be x squared, right? X and x, and the area of the circle is going to be pi r squared. There's my primary equation. All right. Now, the hint in your problem for your secondary equation is right in the first sentence. 4 feet of wire is used to form a square and a circle. So technically, the perimeter of my square and the perimeter of my circle, if I add them up, should equal 4. So let's do a secondary equation to say for x, which is the perimeter of my square, plus 2 pi r, which is the circumference of the circle, equals 4. And then, you know, I really want to solve for x because, I don't know, I like it. And there's less r's to deal with, right? I've got an r squared there. Don't really like that very much. So I'm going to solve this for r. I'm going to say, right, 2 pi r equals 4 minus 4x. And then r equals 4 minus 4x over 2 pi, which equals 2 minus 2x over pi. All right. So now that I know what r is, right, in terms of x, I can plug it back in up there. All right. And again, you can solve for what you want, but I like having the more prominent variable, which seems to me to be x. So I've got area equals x squared plus pi times 2 minus 2x over pi, the whole thing squared. All right, so why don't you pause the video here? Let's take a minute to simplify, and we'll talk about where we're at on the back end. All right, hopefully you did some simplification. I wound up with area equals, I pulled out 1 over pi, and I was left with all right. So if you did not get all the way here, make sure you do. But from here, it's going to be easier to get your critical numbers. All right. Whatever form you leave it in, like I said, you don't have to simplify it as much as I did. You have to simplify it as much as you need to in an effort to get your critical number. So you need to get your derivative, basically. So you don't want to pull out the 1 over pi. Don't pull out the 1 over pi. You know, you want to leave it like this. In order to do the derivative, leave it like that. That's okay. That's your choice. I chose to get down this far. All right, so now we need our derivative. You guys are experts in derivatives. So wherever you left your problem at, why don't you do your derivative, and we'll compare some answers on the back end. All right, hopefully you did your derivative correctly. I get 2 times x plus, excuse me, x plus 4, not x plus 4, just kidding about that, pi plus 4 times x minus 8 over pi. So you see, the pi that I factored out went right back in. Need to set that equal to 0. So we're going to just take our numerator and say 2 pi plus 8 times x minus 8 equals 0. All right, now we got to solve for x. So we're going to 2 pi plus 8 times x equals 8. And then x equals 8 over 2 pi plus 8. Not exactly the nicest critical number you'd ever want, but it is a potential critical number. All right. So, and this is approximately equal to 0.56. So now we can plug in our endpoint. Well, now we got to go back and see if we have endpoints. Well, obviously we do because we have a limited wire, yes? So we have to figure out if let's take our perimeter, because this is the one where we have 2 sides of an equation. And let's say we wanted to put all of our wire into the square, right? The x. And none of the wire into the r, the radius, because there's no wire for the radius. The radius is just a measurement. So let's put all of our wire into the x. So I have 4x equals 4, x equals 1. So the most it could be would be 1. Right? So our domain, right, can't be less than 0 because it's a real thing and it's a length. And the most it could be would be 1. If we put all of our wire into the square, the greatest x could be would be 1. So we would have a perimeter of 4. So now we need a of 0, a of 8 minus 2 pi plus 8. If you wanted to do a of 0.56, you could. Why don't you take a moment, get me all 3 of those values from your area equation right here, and we'll see where we're at on the back end. All right. So hopefully you ran those through the equation. I used a calculator. I do have to admit this would not be an ideal problem for a quiz or a test in my class. 1.273, 0.56, and 1 are the 3 answers I got. So my maximum is here. All right. Which means that all the wire is being used for the circle. All right. So like I said, this is all about the word problem. It's all about the situation. So I can't show you enough situations so you have them all. Hopefully you'll gain more experience with extra practice. But thanks for listening, and I'll see you guys next time.